We know that when we have a flat surface of discontinuity, transmission coefficient is partition impedance, fluid loading impedance, right? And what would be the fluid loading impedance of this kind of plate? And what would be the partition impedance of this plate? For the partition that has a spring and dashpot, this one was minus j omega m s over omega minus plus j. Okay, then what would be the partition impedance of this plate? Minus j omega m, and there's a something that is related with the stiffness of the plate, right? So basically, what we obtained for the partition that has spring mass dashpot and the partition that has this would be same. Let me show you. Okay, this case we have plane wave coming in, reflection and transmission. Okay. Okay. And this has to be oscillating with this magnitude. And that has omega, and this wave number is wave number in this direction that we call bending wave number, KB. Right? And the KB in this direction has to be same as Ki sine theta I. And also has to be same as KB, has to be same as KT sine theta T, to satisfy the boundary condition on the plate. And the transmission coefficient would be similar with what we studied for the partition normal incident and normal reflection. The only difference is this part, fluid loading impedance. So that concludes today's lecture. Therefore, we all finished chapter 3. Now we are ready to exercise what we learned for chapter 3. But I will continue to talk about some physics related with chapter 3, because there are some questions about imaginary angle, and we didn't actually go into the details about the partition that has plate. So we will talk more about those things later on coming Tuesday. So let me summarize what we learned today. We start with the transmission loss of this kind of partition, right? That has spring mass dashpot. Okay. And transmission loss in high frequency region, meaning the high frequency compared with the resonant frequency of this partition, obeys mass law. Low frequency, meaning that lower than the resonant frequency region, obeys stiffness law. But at the resonance, the transmission laws should pretty much dominated by damping. Very obvious. And then we attempted to learn what's going to happen when the wave impinges to the surface of flat surface of this continuity with some angle. And we found that it obeys geometrically the Snell's law. And we learned a somewhat new way to understand the Snell's law by using wave diagram, a wave number diagram, right? And using wave number diagram, we found that there is a possibility that transmitted angle has imaginary angle. And of course, as I said several times, that will be explained later in the coming lecture. And that's the interesting thing, because by interpreting what we observed differently, we found some phenomena that was not possibly recognized in high school year or middle high school year. So the way to see the problem is very important, which I always emphasize. You'd rather see the problem multidimensionally. The other way. What about seeing the problem this way? What about seeing the problem this way? Right? That often guide you to find some new stuff. Okay, and then we expand that concept to find out how much transmission we will get, and we found that the only difference is the characteristic impedance of two medium, oblique impedance, that is simply rho 0 C 0 divided by not sine theta, cosine theta. I appreciate your guys' comment. Right? And then we attempted to expand what we learned to the case for two-dimensional plate case. And again, we use this concept, and we can conclude that the only difference between this and this is the difference of GP, right? So we will go that example on coming Tuesday, and have a nice weekend by enjoying the homework which we provided through our homepage.